Hello everyone, my name is Youhei Akimoto. I'm from University of Tsukuba, Japan. I'm going to talk about saddle point optimization with Approximate Minimization Oracle. Let me introduce our motivational application first, which is automatic berthing control tasks. An automatic berthing control task is a task to control a subject ship toward a target position near a berth while avoiding a collision to the berth. To obtain such a controller, first we design the state equation of the subject ship, where S represents the state vector, A is the action vector, and Y is an Ascent parameter, which, for example, consists of coefficients in the state equation model, weather condition, and so on. Although Y in the real environment, denoted by Y there, is unknown, we need to estimate it to perform a simulation. Let Y sim be the estimated value. Finally, we try to find a controller parameterized by X that minimizes the cost function fxy sim computed through simulation. The obtained controller is supposed to work well on simulation using Y sim. However, due to the difference between the simulation and the real environment, it doesn't necessarily work as well on the real environment, and it may cause a collision to the berth, which must be avoided for safety issue. Now we talk about more general situation. As we saw in the motivational application, we often rely on simulation-based optimization to obtain a solution that is supposed to work well on the real environment. However, it is often difficult to build an accurate simulator, or it is even impossible due to some uncertainty in the real environment. Then, the difference between simulation and the real environment makes the solution obtained in the simulation unreliable in the real environment. A good solution for simulation is not necessarily good for real environment, which is problematic, especially when a low-quality solution tends to have a safety issue. Since we would like to obtain a solution that performs well on a real environment rather than on the simulation, we need to deal with such an uncertainty during the optimization. One way to find a solution robust under the uncertainty is to formulate the problem as a minimax optimization problem. In a minimax optimization problem, instead of estimating y year by a single point y sim, we estimate the set capital Y of uncertain parameter values, including y year. Such an assumption is more realistic than assuming the accurate estimate, meaning that y year equal y sim. Then we minimize the objective function value under the worst scenario y in capital Y. In this way, we can guarantee the performance in the real environment that is upper bounded by the worst case objective value, as long as the real environment is included in the predefined uncertainty set capital Y. In this work, we are going to tackle these minimax optimization problems where the objective function value is computed through simulation, and hence it is black box. Therefore, we assume that the worst case objective function value is not analytically obtained and the gradient is not available. So our objective is to design a derivative-free approach for minimax optimization problems. A popular approach when the gradient of the objective function value is available is a simultaneous gradient descent ascent approach summarized here. It simultaneously minimizes the objective function value with respect to x and maximizes it with respect to y. Here either is the learning rate. This type of approach has been recently popularized by the success of generative adversarial networks, and its convergence properties have been theoretically investigated. For example, on strongly convex-concave functions, where f is strongly convex in x and strongly concave in y, it has been shown that the simultaneous gradient descent ascent converges linearly towards a global optimal solution if the learning rate is sufficiently small. Inspired by the simultaneous gradient descent ascent method, we propose the simultaneous decent Ascent framework relying only on the derivative-free approximate solvers, which is denoted by mx and my. In our framework, in XUpdate, we replace the negative gradient with the difference between the current xt and an approximate minimizer obtained by a numerical solver mx under the current yt. The approximate solution is denoted by mxxtxy. Yt. Similarly, in YUpdate, we replace the gradient with the difference between the current yt and an approximate maximizer under the current xt, denoted by myxtyt. Our research question here is whether we can guarantee the convergence of this algorithm framework as well as we can do for the gradient-based approaches and how fast it converges. One thing that we can easily see from this update formula is that if the approximate solvers are guaranteed to improve the solution over the current iterate every time, then the stationary points of this update formula are all locally minimax saddle point, which are local minimum in X and local maximum in Y. So it's nice. However, whether it converges or not is not trivial to answer. Therefore, we have investigated its convergence property on a relatively simple situation. Here, for the sake of simplicity, we consider the convex-concave quadratic function present here. Since a smooth objective function can be approximated by a convex-concave quadratic function around locally minimax saddle point, we expect that the analysis on the convex-concave quadratic function will provide us an important insight into the algorithm's framework. To guarantee the convergence, we further assume that the approximate solvers mx and my return a solution that is epsilon times closer to the optimal solution under the current solution measured by the squared distance. Then we can show that if the learning rate it is sufficiently small, this approach exhibits linear convergence. From this theoretical investigation, we show the goodness of the proposed approach. However, at the same time, these results indicate that we may need to set the learning rate sufficiently small and the upper bound to guarantee the convergence rate depends on the problem characteristics, which is denoted by sigma here. That is an interaction term between x and y. The more the interaction x and y have, the smaller the learning rate needs to be. Since we are considering a black box optimization setting, such a problem characteristic is not available to the algorithm. This will make the algorithm difficult to use in practice, as it is difficult to choose a right iter. Therefore, we have developed a heuristic approach to adapt the learning rate. In a standard minimization problem setting, we may be able to use the speed of decrease of the objective function value as an indicator for the adaptation of the learning rate, because the objective of the learning rate adaptation is to maximize the speed of convergence. However, in minimax optimization problem, we cannot rely on the objective function value itself, as it is not the amount to be decreased or increased monotonically. Instead, we define a so-called suboptimality error. It is the difference between the worst-case objective function value under the current xt and the best-case objective function value under the current yt. It is known that if f is a convex concave, then the optimal solution of the original minimax optimization problem is the minimizer of the suboptimality error. Therefore, we'd like to minimize this error function as fast as possible. From this observation, we employ this error function as the indicator for the learning rate adaptation. The idea of our learning rate adaptation is as follows. We sample a candidate learning rate around the current estimate of the best learning rate, then learn the algorithm for a while with the selected learning rate, and estimate the speed of decrease of the suboptimality error. If the estimated convergence rate is better than the previously tested learning rate, then update the estimate of the best learning rate. We evaluate our framework. To evaluate the proposed framework, we need to instantiate the approach by implementing the approximate servers MX and MY. For this purpose, we use the so-called 1+1 ES, 1+1 evolution strategy in this experiment. It is a derivative-free approach performing a randomized hill climbing and a step-size adaptation. For each server call, we run the 1+1 ES for iterations roughly proportional to the search space dimension. In this way, based on the theoretical analysis of the 1+1 ES on convex quadratic functions, we expect that the sufficient improvement condition posed in the linear convergence theorem is approximately satisfied with some epsilon. We call the proposed approach using the 1+1 ES as Adversarial Evolution Strategy, AES in short. First, to see how well the proposed learning rate adaptation mechanism works, we tested AES on a convex-concave quadratic problem shown here. The results are summarized in the figure on the left. The vertical axis is the number of function calls until the suboptimality error of less than 10 to the minus 5 is achieved. We tested AES with adaptive learning rate, which is denoted by adapt, and AES with fixed learning rate, where the learning rate is the theoretically derived upper bound, which is denoted by bar eta, times 10 to the power of minus k over 10. And k is the horizontal axis number. We first noticed that the fixed learning rate strategy failed to optimize this problem when the learning rate is equal to or greater than the theoretically obtained upper bound, where the theoretically obtained upper bound is denoted by 0. And we are missing the box here, which indicate that no run succeeded to reach the target threshold. On the other hand, if we set the learning rate smaller and smaller, then the more runtime is required to reach the target threshold. The adaptation mechanism managed to optimize this problem by compromising 2 to 3 times more function calls than the best fixed learning rate situation, which is around k equals 3 or 2. Finally, we compare the proposed framework with 3 existing approaches. Again, we use a convex-concave quadratic problem with different dimensions and different sigma. The left figure shows the result on sigma equals 0. Right figure shows the result on figure equal 2. At the top is dimension 2. The below the result on dimension 10. Here, sigma equal 10 means that the optimal x, sigma equal 0, means that the optimal x and optimal y are determined independently on y and x respectively. On such problems, AES could quickly converge toward the global min-max saddle point, where the result of AES is in blue. On the other hand, some existing approaches fail to converge even on such problems. In case of sigma 2, only AES could successfully converge. These results show the superiority of the proposed approach over existing approaches. In summary, in this work, we have proved a derivative-free framework for minimax optimization. We have proven linear convergence of the proposed framework on a convex-concave function. We have empirically shown existing coevolutionary approaches fail to converge on a convex-concave quadratic problem, whereas the proposed approach successfully converged. We have already extended this work by improving the theoretical guarantee and applying it to the robust Berthing control task that we presented as the motivational application. If you're interested in, please check out our archive paper, where we also discuss the limitation of the proposed approach. This is the end of the presentation. Thank you for listening.